Okay, so today we're going to complete our unit on Dirichlet-L functions. So why are we introducing Dirichlet-L functions? To study primes and arithmetic progressions. Primes and arithmetic progression is just the first of many things you could look at. Prime triplets, p, p plus 2, p plus 4. This one is boring. Why is p, p plus 2, p plus 4 boring? So p, p plus 2, p plus 4, boring. And why is this boring? Well, I want these three numbers to all be prime. Why is this? I'm sorry?
357.
Yeah, the only one is 357. Why is there no other example? 3 is going to have to divide one of these. If this is a multiple of 3, you're dead, unless it's 357. If this is congruent to 1 mod 3, then this is 0 mod 3. And if this is 2 mod 3, then this is 0 mod 3. So when you look at more general things rather than just primes and arithmetic progressions, you could look at prime pairs, prime triples. You have certain arithmetic constraints. So essentially, don't do stupid things. Don't do stupid things. And the circle method will actually quantify this. That if you try to do stupid things, the circle method will tell you that the main term is 0. That it will not be able to predict how many examples you have of something. One of the inputs we're going to need in the circle method is counting primes in arithmetic progression, which is one of the reasons we're doing the course in this order. All right, so this is another AA lecture. 5 steps to there exists a P congruent to A mod M if AM equals 1. So like many theorems in mathematics, this is due to no, Dirichlet. Yeah. Dirichlet has a lot of good theorems. Chebyshev has a lot of good theorems. You'll see those names very frequently in classes like this. All right, so there are 5 steps. So step 1, the log of LS chi is equal to the sum over P. The sum k goes from I think 1 to infinity of chi p to the k over k p to the ks. So we discussed this last time. And what did this come from? It comes from 2 things. So, Euler product. And what else? Nope, geometric series. Orthogonality relations is later when we sum. But I like that orthogonality is on people's mind. Geometric series. So if C 1 over 1 plus or minus blah, think geometric series. So whenever you see something that looks like 1 over 1 minus blah, the geometric series should be in your mind. And for us, blah is equal to chi of p, p to the minus s. And that's why we have an expansion like this. All right, so this is step 1. Step 2 is now to do some kind of averaging. So 1 over phi of m, because that's the number of characters we have, then the sum over the characters mod m of chi of a log of ls chi is equal to the sum over p, sum k goes from 1 to infinity. And I'm going to just bring the sum of 1 over phi m, sum over chi m inside. We talked about this last time. When I bring this inside, now I use the orthogonality relations to say if p to the k is 1 mod m, I'm summing 1 for every single character, and I get phi of m. Phi of m divided by phi of m is 1. If, however, this p to the k is not 1 modulo m, when I sum over all characters, I get 0. If m is a prime, it's particularly nice. You can write things down with the geometric series formula. So what we'll get is we'll sum over all these such that p to the k is congruent to 1 mod m. And we get 1 over k p to the ks. So this is a really nice expansion. Remember, what is our goal? What are we trying to do? And what do we want to do when we look at these primes? What's our objective? To show they exist. Just one. Right? We're not trying to get the best estimate. How should you count primes?
With relish.
Not with relish. With what? It is one of the only ways you're allowed to discriminate on this campus without getting into trouble.
Weights.
With weights. What weights do you put on primes? The logs. We don't have any log p weights here. The way we would get a log p weight is we would take the logarithmic derivative. We've just taken the logarithm. If we take the logarithmic derivative, we'll get an L prime over L. And then we'll hit it with a test function. We'll do a contour integral. We'll use a lot of tools from complex analysis. We'll get a much better result. Right now, we're not going for a good result. We are going for the weakest possible non-trivial result. There is a prime. Now, unfortunately, Dirichlet is too clever to just get one prime. He will actually give us infinitely often. And he will give us so many that we will get that the sum of the reciprocals diverge. But we won't quite know exactly what the count is up to x. There's a little bit of issues in passing back and forth. All right, so that's step 2. So step 3, so if we look at the right-hand side above, is the sum over p congruent to a mod m of 1 over p to the s plus big O of 1 if the real part of s is greater than or equal to 1. And so what we're doing is we're just looking at, well, what is the contribution from k goes from 2 to infinity over all primes? And so the error, the big O term, of 1, this is from the sum over p, the sum of k greater than or equal to 2, 1 over k p to the k s. This will be less than or equal to the sum over all integers greater than or equal to 2, the sum of all k from 2 to infinity. We can even drop the k over there. S is going to be at least 1. This will be 1 over n to the k. Which sum do you want to do first, the k sum or the n sum? The k sum. Why do you want to do the k sum?
We have a formula for it.
We have a formula for it. It's the geometric series. So if we do the k sum first, this is going to be the sum n goes from 2 to infinity. Now the first term is 1 over n squared, and then 1 minus 1 over n. Well, what can you say about 1 minus 1 over n? N is at least 2, so the largest the denominator can be is 1/2. So this would be, in fact, I can replace this with a 1/2 at the cost of making things a little bit larger. And now we know the sum of 1 over n squared converges. So this is now less than infinity. And again, we don't care particularly what it is. It's just some finite number. And so as long as it's a finite number, we're fine. What this is telling us is most of the contribution is coming from the k equals 1 term. This is very similar to a lot of things we've seen in counting primes. We've seen for other things that it's convenient to have the prime powers together. This gave us the lambda function. And if we try to count the primes up to x, what are the contributions from the prime squareds? Well, imagine every single perfect square is a prime. How likely is it that every single perfect square is a prime?
0.
Okay. How likely is it that every perfect square is the square of a prime? If we're only counting up to x. Is there any x where every perfect square up to x is a prime? Which one? Yeah, it depends on what you do with 1. So 1 is going to throw things off even in the beginning. If you don't consider 1 causing trouble, maybe if you take all the perfect squares up to 4, you'll be fine, and every one will be a prime squared. If you go up to 9, everyone's a prime squared. But as you start to go higher, eventually you get things like 36. So not every perfect square is a prime squared. If we just trivially estimate the number of primes, such that p squared is less than or equal to x, how many of these are there? We could just trivially estimate it by square root of x. That's much, much lower than the number of primes. So in all of these arguments, the prime squareds, the prime cubes, the higher powers of the primes, they don't really matter. It's frequently better to just keep them in. It just gives you a little bit nicer quantity to count. Now at the end of the day, if you want to know how many primes there are, you do have to remove them. And you can often do some kind of inclusion-exclusion. If you know how many primes there are and you have a really good formula for that, well, to figure out how many prime squareds less than or equal to x, that's the same as how many primes are there less than or equal to square root of x. And you can play games like this, passing back and forth. And your error term is going to be so small from this, it's not going to be that big of a deal. All right, so we've done 3 of the 5 steps. So step 4. So what we want to do now is we want to look at the very special character LS chi naught. So chi naught is the trivial character, or the principal character. It's the one that sends everything to 1 that it's allowed to send. Okay? The things it can't send to 1 are the numbers that have a common factor with m. But other than that, it sends everything to 1. So what does this look a lot like? It looks a lot like the zeta function. And it turns out it equals the zeta function times the product over all primes dividing n, 1 minus p to the minus m. And what we're doing is we're balancing and we're removing basically just a couple of factors. And so now if you put those in here, when we look at the Euler product, we have a product over all primes that don't divide m. And so if you now you turn this into a series expansion, any term that has, any n that has a prime dividing m will no longer show up. So with a little bit of algebra, you can see these two are equivalent. So in terms of the behavior, does this have a strong effect or a weak effect on the behavior?
That does divide m or doesn't divide m?
Over here, it's the primes that divide m. I'm canceling those from the zeta function. And now when I expand, I'll be left with the product over primes that don't divide m of 1 minus p to the minus, it should not be minus m. It should be minus s. So you think this has a strong effect or a weak effect? A weak effect. This is a finite product. As s goes to 1, as s goes to 0, it doesn't matter what s is doing. This is well behaved, right? So that is going to have absolutely no effect as to what's going on. So what can you say will happen is the limit as s goes down to 1 from above of ls chi naught? What do we know about this?
Should blow up.
It has to blow up. The only way it wouldn't blow up is if somehow this goes to 0. Well, it's a finite product of things that are very close to 1. So a finite product of things close to 1 is not going to go to 0 and counteract. All right, so far, does this seem that bad? So we've saved the worst for last. So step 5 is the big one. Assume L1 chi does not equal 0 for all chi. Then there exists infinitely many primes congruent to A mod m. So the last one is the big step. Why does this apply? So return to step 2. So in step 2, let's see if I can get over here. We have this product over here on the left-hand side. We chose this A. Oops, this should be 1. We chose this A precisely because we wanted to study primes congruent to this should be a chi bar of A. We want to study primes congruent to A mod M. So this was a really good choice to make. There are other choices of A that are good. Can anybody give me another good choice of A? So we saw in Monday's class that if we take chi bar of A, if we multiply by chi of p to the k, we combine things, it becomes chi of A inverse mod M times p to the k. If A inverse times p to the k is 1, then that means p is congruent to A mod M, and that's exactly what we want. There's one other choice of A that's useful. And if you think about it, there's only one other natural choice of A. That's the same as negative A. What's a good choice of A to take? What's a choice of A that might be easy to analyze? What's the simplest A I'll let you get away with? What's a choice of A that I will not let you get away with? 0. I'm not going to let you choose A equals 0. Why won't I let you choose A equals 0? Yeah, just 0. And so you're going to get no information from that. So you've got to choose something useful. You could choose 1. So if you choose A equals 1, the hope is that maybe that could give us something useful. And so if we choose A equals 1, that's going to give us 1 over phi of m, sum over all chi mod m. Now we get the log of L s chi. If we take s to be a real number, this is essentially going to be related to the size of things. Imagine we know that L1 chi does not equal 0. It's not hard to show that it doesn't have a pole either. So if it doesn't have a 0 and it doesn't have a pole, what can you say about these quantities? The log of the LS chi's. They're finite. Are they finite for all characters, or is there a character we have to be careful about? The principal character. The principal character, the trivial character. If we put that in, it's essentially the Riemann zeta function. It blows up. All the other ones, because we're assuming it's not 0, the log is going to be a finite number. What can you say about this quantity? It has to be tending to? So under... 1. Not tending to 1. So we're assuming that none of these characters equals 0 or have a pole when s equals 1. So the log of all of them are finite, except for the trivial character, whose logarithm is going to infinity. So infinity plus a bunch of finite numbers is infinity. So what this tells us is, goes to positive infinity as s goes down to 1 from above in the reals. This is actually very useful in terms of studying what goes on. Imagine L1 chi equals 0. If chi does not equal chi bar, L1 chi equals 0 implies L1 chi bar equals 0. So this is going, if you look at the series expansion, if you just take complex conjugates, what is the complex conjugate of 0? 0. So if L1 chi equals 0, take the complex conjugate, you get L1 chi bar is 0. And so now when you look at what's going on here, you'll have two zeros. The logarithm, well, the sum of the logarithms, that becomes a product. If I have L1 chi equals 0, L1 chi bar would also be 0. If chi does not equal chi bar, I would have two factors of 0. I only have one pole. Not only is it finite, it's worse than finite. It's 0. And so this side would be going to negative infinity. So you would have this side going to negative infinity. Now let's go back over here and look at step. Okay. So if we come back over here, what can you tell me about the sum on the right-hand side when a equals 1? Summing over p, summing over k, p to the k is congruent to 1 mod m. 1 over k, p to the k, s is tending to 1. What do you know about this sum? Non-negative, right? That's more than enough. It's non-negative. If an L1 chi equaled 0 and chi did not equal its complex conjugate, this side is going to minus infinity, this side is non-negative. There is no way minus infinity can equal a non-negative number.
But what if you use infinitesimals? That's true.
Yeah, I'd have to say that it wouldn't be funny. But there's no way negative infinity. I was trying to think about, well, we have some of the zeta functions, we add all the numbers and we wrap around, and we look at zeta of negative 1, we sum all the positive integers and get negative 112. But that's an infinite continuation. And so this is from 2, left-hand side goes to minus infinity as 2 zeros or more and 1 pole. But right-hand side is greater than or equal to 0, contradiction. So we're almost done. So why do I claim that this implies that there's infinitely many primes? Well, if we come back over here, you're again looking at step 2. Now we go back to choosing the A we want. We know all these other characters, when I take s equals 1, the logarithms is finite. What can we say about the left-hand side? The left-hand side is finite? Unless you're doing like a Three Amigos joke along the lines of El Guapo being infamous. It's infinite, right? We know that all the characters have finite logarithms except for the trivial character. So because of that, the left-hand side is going to infinity as s goes to 1. If we look at the right-hand side, we have this sum. We want to show that there's infinitely many primes. Maybe we're just getting a lot of contributions from 2. Maybe 2 is contributing, and then 1 over 2 squared, 1 over 2 cubed, 1 over 2 to the 4th, 1 over 2 to the 5th. Well, that can't happen because by step 3, we showed the right-hand side is the sum of the reciprocals of the primes at s plus something bounded. So the contribution from all the other prime powers is negligible. So because it's bounded like this, the only way we can have this infinity equaling this as s goes to 1 is if there are infinitely many primes. So Dirichlet's argument proves not only are there infinitely many primes, we actually get that the sum of the primes diverge. The sum of the reciprocals of the primes diverge. So Dirichlet, now it's steps 2 and 3, gives the sum of 1 over p diverges. And that's a wonderful result to have. Yes?
I was wondering how we know that if there are 2 zeros, that makes it so the logs go to negative infinity. Like how do we know that those 2 zeros cause to go back much over power of the trivial character?
Well, if you think about what's going on, the trivial character has a simple pole at s equals 1 of order 1, residue 1, or well, maybe not residue 1, but has a simple pole at s equals 1. So when you look at the logs and you combine everything, this is going to look something like a product, if I exponentiate, of L s chi. And we'll take a product over all chi mod m. From the trivial character, we're going to get something like a over s minus 1. And then from the 2 characters where we have a 0, we'll get a b1 s minus 1, a b2 s minus 1, and then we have the remaining characters times the rest. And so now these cancel, and now this product is tending to 0. Since it's tending to 0, the product tends to minus infinity.
You mean the sum of the logs?
Well, the sum of the logs tends to minus infinity. And so that's the contradiction. So what's nice about this is we can very easily prove that all characters have L1 chi not equal to 0, except possibly characters where chi equals chi bar. And it turns out that there is at most And in fact, exactly one real character where chi equals chi bar for each n. And the whole difficulty now comes down to showing that that L1 chi does not equal 0. The other characters are very easy to handle. The hardest part in Dirichlet's proof was showing that you could handle the case when you had a real character.
Is that the one that sends everything to 1? Or if it sends...
Well, you just have to show that if chi is a real character, L1 chi also does not equal 0. And this is what led to the Dirichlet class number formula to handle something like this. And this was a major achievement. It connects analytic number theory with a lot of good stuff in algebraic number theory, with class numbers, lots of great stuff. So I don't want to go into full details. I want to talk a little bit about how do you prove something is not 0, and I'll do one case just to convince you. So proving L1 chi does not equal 0 if chi equals chi bar. It's very, very hard to prove something equals 0. How would you prove a sum is exactly equal to 0? Well, let's say you do some numerics. You believe the sum is exactly equal to 0. You do some numerics. You sum the first googolplex terms. And you get that it's equal to like 1 over googolplex squared, looking a lot like 0. Is this going to prove that it exactly equals 0? No. You can't prove it's exactly equal to 0 by something like this, because maybe it's just a little bit away from 0, and you just happen to be within that uncertainty. Look at it this way. If it is actually equal to 0, then whatever you got is from a truncation, and then you're within the uncertainty, you're within the error. You're within the numerical approximation. There is no way to numerically approximate an infinite sum with finitely many terms and prove that the infinite sum is 0. You can always change the sum many, many terms down the line. And if you change it by a little bit, you'll change the value. So in general, we don't have that many techniques to prove something is non-zero. I'll say one of my favorites. Sometimes no equal alpha p over q, pq integers q, q will be positive, 0 less than q less than big Q. Imagine you have a situation like this and alpha is known. This happens with elliptic curves. So we're probably not going to get to elliptic curves this semester. But you can form L functions from elliptic curves. You look at y squared is x cubed plus ax plus b. A and b are integers. You look at y squared is congruent to x cubed plus ax plus b mod p. And you use that, I'm not going to say exactly how, to get some numbers ap. And then you use those APs to build up an L function. And then you can ask questions about that L function. Does that L function vanish at the point 1? And in those situations, it turns out we know it equals something like this. So imagine we know it is pi times p over q with 0 less than q less than 100. Pi is probably a bad number because that might make you think of products. I'll do square root of 2. Another nice number. What kind of numerical calculation can we now do to show that it is exactly equal to 0? So again, it's huge to know something like this. We don't always know something like this. These are major results in mathematics. But we do know this in situations. We do know this for elliptic curves. Any thoughts about how you can use this to improve upon itself and prove that if it's sufficiently close to 0, it must be 0? Not quite. So imagine, calculate and get x plus big O plus an error at most square root of 2p. I'm not going to take the best thing. Imagine I get something that looks like this, roughly square root of 2 times 3 over 100. Let's see. So times 3,000. And then the 3's will cancel. So imagine I get something like this, square root of 2 over 3,000 plus an error at most square root of 2 over 1,000. Is the error large enough so that this could be 0? Yeah. So it's large enough so that it could be 0. I know my numbers are the form square root of 2p over q. The smallest I could be that's not 0 is square root of 2 over 100 or negative square root of 2 over 100. If I can show here's 0, here's root 2 over 100, here's negative root 2 over 100. I just need to do my calculation that when I truncate it, I need to show that my truncation cannot reach this number. If it can't reach this number, the only number could be a 0. And then all of a sudden it improves itself. So this is one of the best ways we have of calculating. There we go, I gotta figure out how to do it. This is one of the best ways we have of calculating whether or not a number is actually equal to 0. In order to actually do a full calculation and actually prove a major theorem, I thought I would choose 1m and actually calculate L1 chi when chi is a real character. So the question is, which is a good choice of m? What's the best choice to use? Any thoughts? 2. Well, the problem is if I use 2, 2 is too easy. Because the problem with 2 is, what are the only numbers relatively prime to 2? 1. And I have to send 1 to 1. So I have no freedom. So I need a number, m, such that phi of m, the number of numbers relatively prime to m, maybe is 2. I could try 3, but what else could I try? 4. No, 12 is too big. 12 has, there's 4 things relatively prime to 12. There's 1, 3, 5, 7. No, I'm sorry, 1, 5, 7, 11. All right. Let me do 4. If I do 4, what's nice about 4 is things break into evens and odds. Things are very nice. We have good. So L1 chi does not equal 0 for chi, the real quadratic character mod 4. So there are 2 characters. There's the trivial character, chi of 1 equals 1. What's the other value of chi I need to evaluate? 3. I'm going to, instead of 3, I'll write negative 1. That's just the more common way people write the numbers modulo 4. It's 1 and negative 1. And what will chi of negative 1 equal? Sorry, this is the trivial character. I'll put a 0 to minus those. We're talking about the trivial character right now.
0.
Nope. 1. Right. The trivial character sends everything to 1. That it can. Right. If it shares a common factor with them, it's not going to send it to 0. But anything else it sends to 0. Sends to 1. So chi naught of 1 is 1. Chi naught of minus 1 is 1. Now let's build the other character, the real quadratic character. There's not that many possibilities. What is chi of 1 going to be? Has to be 1. And chi of minus 1 has to be minus 1. Why does it have to be minus 1? It's a group homomorphism. We've got to send it to one of the second roots of unity. And there's only 2 roots, it's 1 and negative 1. If we send it back to 1, we've got the trivial character again. So now we look at L1 chi. So this is going to be a sum, and it goes from 1 to infinity of chi of n over n. Well, the only ends that survive are the ends that are odd. Right? And it's going to alternate 1, -1, 1, -1, 1, -1. So we get 1 minus a third plus a fifth minus a seventh. Anybody ever seen this in a police lineup? Pi over 4. Excellent. It's pi over 4. Where does the pi over 4 come from in this? I'm sorry? We could do it through Fourier analysis, which would be kind of fitting in this class. There's lots of ways to get pi over 4. There's actually a name for this expansion for pi over 4. Anybody remember the name of this one?
The alternating sign reciprocal of odd numbers expansion.
Yes, which is abbreviated the Gregory Leibniz. Okay. Anybody have any thoughts as to where this might come from?
Taylor series.
Of what?
One of the trig functions.
Which one? What trig function do you think is playing a role here? I'm sorry? We've got a pi over 4. What do you think is playing a role here? Not the arc sign. Arctangent, right? What's the derivative of arctangent of x? 1 over 1 plus x squared. We've seen this function at least once in this course. And we've talked about integrating it. We've talked about why the derivative works. We've talked about the Cauchy distribution, why this is such a great normalization factor. So let's integrate from 0 to 1 of 1 over 1 plus x squared dx. This is just arctangent of 1 minus arctangent of 0. So the arctangent is what angle has a tangent 1? This means the sine equals the cosine. That's pi over 4. We always do things in radians. What angle has a arc has a tangent of 0? Just 0. So that direction is no problem. The other direction, how should we handle the other direction? What should we do?
Sorry, which one?
Well, we somehow have to relate this to that, right?
Okay.
Right? We've got this integral equals that, so we just want to show that this integral equals this as well. This is very similar to one of your homework problems. Geometric series. Why geometric series? Yeah, we have 1 over 1 plus x squared. As soon as we see that, we should be thinking geometric series. Thinking might even be the wrong word. We should just be saying geometric series. It should just be immediately on our mind. We have a reciprocal of something of the form 1 plus blah. Right? Here, r is equal to x squared. So this is the integral from 0 to 1 of the sum. N goes from 0 to infinity of negative x squared, x to the negative 2, to the n dx, as r equals negative x squared. X to the negative 2, sorry. And remember, when we have the geometric series, we want 1 over 1 minus r. So I need to write 1 over 1 plus x squared. So we want it as 1 over 1 minus r. So r is equal to, oh, wait, sorry, there's no negative sign there, sorry. So r is equal to negative x squared. All right, now what do we do? Switch. So now I get the sum, and it goes from 0 to infinity, negative 1 to the n, integral from 0 to 1, x to the 2n dx. All right, the sum, and it goes from 0 to infinity, negative 1 to the n. When we integrate x to the 2n, we get 1 over 2n plus 1, and then the bounds will cancel. And that will be 1 minus a third plus a fifth minus a seventh. And there we go. Anything troubling? So the absolute value of r has to be smaller than 1, and it's not. Yes, that bothers you? OK. So you actually want to use theorems where they're applicable? OK, yes. Very good habit to have. All right, so that's one problem.
Why is the absolute value of r small?
When x equals 1. So unfortunately, as has been pointed out, we can't use this formula. Issues.
Then 0 to 1 minus epsilon.
Right. So when x equals 1, the absolute value of r equals 1, and that's bad. So you can do integrate from 0 to 1 minus epsilon and send epsilon to 0. So if we do that, everything will be OK.
Aren't you allowed to just disregard a point?
Yeah, but we're integrating all the way up to 1. And so the way we should really do this is we should break the integration up at 1 minus epsilon. And then r is strictly less than 1 and bounded away. Now, if you look at what happens, if you actually take x equals 1, we have 1 over 1 plus 1 squared is 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. What's the sum on the left? 1/2. What's the sum on the right? Not anything. Only two possibilities. 1 or 0. If I stop after an even number of terms, I get 0. If I stop after an odd number of terms, I get 1. Let's split the difference. As 1 if stop after odd number of terms, and 0 if even, split the difference.
So is that a thing, like taking the expected value of
There's a whole series of techniques in something like this. This will lead to a Bell summation, this is our summation. There's whole slews of techniques to make sense of something like that. And what's nice is, what's really going on is we have 1 over 1 plus x squared is 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus dot dot dot. This makes sense as long as x is less than 1 in absolute value. We can then take the limit as x goes to 1. And the limit actually, on the left-hand side, is well defined. The limit is 1/2. This is the analytic continuation of the geometric series formula. The place where we don't want to analytically continue the geometric series formula is when r equals 1. Really, this is not r equals 1. It's r equals...
anything within a small...
What does r equal for this problem? It's not r equals 1. Negative 1. R is negative 1 here. So really, when we look at what's going on here, we're not putting it in at a place where the function has a pole. We're putting it in another place. And it turns out everything is OK. So again, I just wanted to do this to get you this on your radar screen. I'll put some comments about various summations like this, where you can take things that diverge and somehow work and get something out of it. I mean, if you had to assign a value to this sum, isn't 1/2 a reasonable thing to assign to it?
Well, sure. The probability of stopping at 1, the probability of stopping, or at an even term and odd term.
Yeah, I mean, you're going to stop randomly at some point. I mean, half the time you'll stop at an even, half the time you'll stop at an odd. Split the difference. All right, any other issues? That was the first issue.
Justifying the interchange.
Always justifying the interchange, right? So next issue. Does the integral from 0 to 1 of the sum over n equal the sum over n integral from 0 to 1? What makes this interchange a problem that needs justification?
sign?
We have alternating sign. No, it's more than alternating sign. If it was just alternating sign, I could justify. There's something going on here that requires justification.
Backward going from n equals 1 to infinity.
Then we have it going to infinity. N goes from 0 to infinity. If we only had a finite sum, it would be okay. Finite sums we can interchange with a finite integral. Whenever there's an infinity, we have to be careful. But the geometric series has a beautiful property that is not shared really by anything else. What is that beautiful property? No, lots of things have absolute convergence. That's going to require me to roll up my sleeves and do technical arguments.
We have a closed form.
We have a closed form for the... There's lots of infinite sums that have closed forms. What's great is that we have a closed form not just for the original geometric series, but also for... Nope. So what we want to do is we want to expand this with an infinite sum. We can't deal with an infinite sum. So we'll take a finite number of terms, and then we'll have a tail. And it turns out we have a closed form expression for the tail. So 1 over 1 plus x squared, we can write this as a sum. N goes from 0 to n minus 1 of x to the 2n plus x to the 2n over 1 minus x. And this is using the closed form of the sum of a geometric series. Because all that's really going on here is we just pull out one of the terms, and then it's like we've started all over again. We now have only finitely many terms. Because we have only finitely many terms, now we can interchange the integral and the sum. This part is going to begin to look like the very beginning of our series, and then this part over here is going to be easily bounded. And in fact, if you look at the series we have, we have an alternating series of decreasing magnitudes. What can you say about an alternating series of decreasing magnitudes? It's bounded by the first term. Because what's going to happen is, if I stop over here, I add on 1/9, and then I subtract a little bit more. I'm sorry, I subtract a little bit less. And if I look at what's going on, I subtract 1/11 and I add 1/13. Well, minus 1/11 plus 1/13 is going to be negative. Then minus 1/15 plus 1/17 is going to be negative. So if I pair everything up now in groups of 2 from the 1/9 onward, it's always going to be negative. And so this is one of the nice things about an alternating sum, where the terms are decreasing. So alternating sum, absolute values decrease, converge. And really what we can do is we have 1/9, then we have minus 1/11 plus 1/13, and this will be negative. Then we have minus 1/15 plus 1/17, this will be negative. And so we know if we go all the way like this, we're never going to get higher than 1/9. So whatever our truncation is up to here, from this point onward, we're never going to add more than 1/9. We can group the other way. We can group it as 1/9 minus 1/11 plus 1/13 minus 1/15. And now what can you say about this? It's positive. And this is, so we know we'll never be below what we get when we truncate here. So this is the really nice thing about alternating sums with decreasing magnitudes, is if we truncate, we know upper bounds and lower bounds for where we are. And since these upper and lower bounds are going to be tending to 0, we know the sum has to converge.
But that only shows that like after every 2 terms, you're not below what you were at before. Because you have to group, because you're grouping the terms.
Mm-hmm.
What if like in between, what if when you...
But then just one, I mean, even if I just do one term, it's not going to make a difference. Because the individual terms are going to 0. And then every time I take 2 of them, it's going to be going in the same direction. And that's the main thing, is when I truncate, you are absolutely right, I might truncate here, and I don't have the thing to pair it with. But I could add that back if I'm missing it because it's going to be so negligible. And it's going to be something small. So this gives you a flavor of how you can attack problems like this. This is a very special case. In general, we are not fortunate enough to be able to do a special case like this and calculate things out explicitly. But if I give you a Dirichlet L function and I give you the character, you can just calculate the beginning of the character by brute force. And then eventually you can bound what the error term is. And so if you can just show that it's far enough away from 0, you're fine. Now you have to do this for all the characters, and this becomes a bit involved, but it's doable. Dirichlet has a beautiful result, and this is the class number formula that gets you this for all the stuff. All right, so this finishes up our unit on Dirichlet L functions, and from this now what we're going to do is we will now